So yesterday we had an experimental design type lab question where we were told to determine experimentally the rotational inertia of this pulley right here, which they can't see. This pulley right here. It is not a perfect cylinder, as most pulleys aren't. A lot of pulleys you can kind of approximate, but this one has a pretty deep groove in it. And so you can't just use 1/2 mr squared for the rotational inertia of the pulley. You have to experimentally determine it. And that's because there's a pretty deep groove cut into it, and so it's not a solid uniform cylinder. So to experimentally determine the rotational inertia, we need to solve these equations for I, where we can either eliminate all the other variables or have them be known values. And of course, I forgot to pull up Logger Pro because we're going to run the experiment one more time.
I don't think they finished it. I think like you had all the numbers in it.
Yeah, I was running through it. So we're going to run the experiment one more time so I can have the updated or the most recent experimentally determined value for the acceleration. Okay, and so we knew, it's a good thing the custodian didn't pick that up. So we knew, I made some measurements of things before class even started. I made a measurement of the mass of the cart, because these are things that are very easily measured. Mass of the cart was 490.1 grams, or 0.4901 kilograms. So the mass of the hanger was 0.0498. kilograms, or 49.8 grams. The effective radius of the pulley, not the overall radius, but I drew this wrong. Oh my gosh. Look what you did, Julian. Disappointed. So this is the actual inner radius where the string is actually looped over. But if you look at the pulley, that's what it looks like. Okay. But the lever arms, the radius on the pulley at which the tension forces actually act are at this distance. I'll call that RP. So on my diagram, these would have length, that same length. And that I measured the actual radius of the pulley, and then I dropped my ruler down in here to measure that distance and subtracted them and got the pulley radius of 0.018 meters. So that's most of our knowns. I got these three equations up here with the unknowns being the tension force 1, the tension force 2, the rotational inertia, and before I run the experiment, the acceleration. But then I can run the experiment to determine that acceleration. Why is it not recognizing? Why doesn't it see the motion detector? Oh, come on, Logger Pro. There we go. So now we'll experimentally determine the acceleration just like we did yesterday by creating a velocity versus time graph. Oh my gosh. As you can see, my life's kind of a mess right now. I had to make an electromagnetism demonstration video before school today, and there's entirely too much stuff up here at the moment. Okay. Let's run the experiment. Hello? What's going on? Not responding. Jillian, this is all your fault. Okay, Logger Pro's being a butthead. So, Can you guys tell me what our experimentally determined value for acceleration was yesterday? Do you want to write that down? Hopefully. You don't take notes, Carson?
I did not write down that specific number.
Do you not take notes at all, though? I see nothing on your desk.
I'll just look at the packet.
Okay. Yep.
Is 0.79?
Yes, that's what it was. 0.7932
932.
meters per second squared. You know, it's not a great habit, right? You're not always going to have teachers that give you packets of notes. I am told that I have to give notes out to my students. You're going to have college professors who literally stand in front of the class and talk for an hour and expect you to know it when it comes test time. Of all classes, you should be taking notes in physics class as I work through solutions. Because you know how often I hear, you know, Mr. Graham, it looks so easy when you do it, but when I sit down and I try to do the same types of problems, I struggle. Yeah, because you're just watching me do it. You're not actually physically doing it with me. I'm telling you, man. I'm telling you. You're shooting yourself in the foot. Okay, so now I have everything except for those three unknowns. I have a system of three equations. We know how to solve systems of equations. I have solved both of these equations for the tensions, which then I can substitute in for those, eliminating those from my final equation, and solve that for our rotational inertia. So when I do that, substitute for F2, the tension 2, I get mhg minus mha times the lever arm, which is r sub p if you want to put that in there. Yes, that must distribute, right? You must be careful there. Minus tension 1, which is mass of the cart times the acceleration, times r. And that's going to equal rotational inertia times a over r. Since we are looking for the rotational inertia, I need to get rid of the a and the r on this side. So I multiply both sides by r over a. And then I multiply this entire side by r over a. Must distribute, if we were going to do it that way. And if I do that, my rotational inertia is now by itself. And so I have rotational inertia is equal to the lever arm for the pulley divided by the acceleration times mass of the hanger times g minus mass of the hanger times a times the lever arm minus the mass of the cart times the acceleration times the lever arm. And then I work that out, and that should give me my result. So the physics is done. This is arithmetic. This is calculator work. This is easy. So I get 0. It's easy. Also easy to make a mistake, though, so you got to be careful. Divided by our acceleration, especially with all these decimal numbers. Times mass of the hanger. So the hanger, 0.0498. Times g, 9.8. Minus mass of the hanger, 0.0498. Times the acceleration, 0.7932. And then all that's like this, right? Times r. So times 0.018. So that's times r. Wait a minute. Am I missing something? Mass of the hanger. G minus mass of the hanger. Acceleration. Times r. Minus mass of the cart. 0.4901. Times the acceleration. 0.7932. Times lever arm. 0.018. Outer bracket. Okay, I think that's right. Yes. All right. Hopefully you can do that in your head. If you can't, then you're behind at this point. Dude. You know what happens if an administrator looks in and sees you with your mask off and sees that I'm not telling you to put it on? You know what happens? I get crap for it. You think I want to get crap because you want to refuse to wear your mask? No. 0.0498 times 9.8 minus 0.0498 times 0.7932. All that times 0.018 equals that. Minus 0.4901 times 0.7932 times 0.018. All that times 0.018 divided by 0.7932. And I get a very small number. Did you get a small number? Yeah. So my rotational inertia of that little pulley is, I got 2.44 times 10 to the negative fifth. Negative fifth. And remember the units, mr squared, m kilograms, are meters squared. No special name for that. Kilograms times meters squared. That pulley has a noticeably larger rotational inertia than these little smart pulleys. This is a lot lighter and a lot less mass. So what this tells us, and we'll do some you'll do some problems where you'll have rotational inertias that are, a lot larger than this. What this tells us is that if this has a rotational inertia that's really, really small, then it doesn't have much effect on the whole thing. Then this guy pretty much acts like an ideal pulley, and that's valid. Okay, it's not until you get to actual much larger pulleys where the rotational inertias of those pulleys start playing a more significant role in the physics situations. Cool beans? All right, any questions about that? Again, this is difficult to not mess up on. I was definitely expecting either myself or Mr. George to have probably more myself because I'm doing it on a calculator like this, but yeah. So are we good with that? Okay. So we're gonna do one example problem. Example 3 from your notes. This is kind of like an Atwood problem, but without a mass on the other side. Some problems that are similar to this one are like yo-yos. When you got a yo-yo, when you got a spool of thread that's being unwound. On one of my AP teacher training sessions that I went to over summer, one of those summer institutes, we had a competition where we were each given a roll of toilet paper, and we just hold the toilet paper up there and then let go of it, and it would unroll on the way down. And it doesn't move down like it would if you just dropped it, right? Because there's a tension force from the toilet paper pointing up that actually creates the torque that causes it to rotate when it goes down and reduces the rate at which it falls. And so our competition was determine how long it takes for that toilet paper to hit the ground. Whoever gets the closest got a piece of candy or something like that. So these are all kind of similar. You approach those all in the same way. In this particular problem, we have a uniform solid cylinder of mass m equals 1.5 kilograms. And it's a cylinder, but it's like a pulley, right? So it's a uniform cylinder like my regulation-sized hockey puck right here. Okay. Uniform cylinder. Solid disc. Disc, cylinder, same thing, like we talked about yesterday. So we got a uniform cylinder of mass, and this is capital 1 equals 1.5 kilograms, and then lowercase m is the hanging mass. My capital M's and my lowercase m's look the same. So I'm going to say mass of the cylinder. You say MP for mass pulley, whatever you want. Mass of the cylinder is 1.5 kilograms. And radius, capital R, remember you can use capital or lowercase r, doesn't matter. Capital R, 0.25 meters, is mounted on frictionless bearings about a fixed axis. The rotational inertia of the cylinder about its axis is I equals 1/2 mr squared. Again, you don't need to memorize those. You'll be given those if you need to use them. Okay, so the rotational inertia for the cylinder is 1/2 mass of the cylinder times its radius squared. For any uniform cylinder, any uniform disc, a pulley that you can approximate as a disc or a cylinder, that will be true. A block of mass little m, so I'll call this the hanging mass, so mh, of 75 grams or 0.075 kilograms. It's suspended by a cord wrapped around the cylinder and released at time t equals 0. On the diagrams below drawn, identify all the forces acting on the cylinder and the block. All right, so let's do the block first because that's the easy one. The block will not be rotating. So the hanging mass will not rotate. They're calling it the block, so I'll say MB, mass of the block. It's not rotating, so we don't draw a rotational free body diagram. We just draw a free body diagram like we did back in the day. So what forces are acting on the block? Tension. Which way is the tension point? Up. And since we're not going to have multiple tensions, we can just have one single tension. Are you live, Will? You live? You getting enough sleep, man? You get more sleep. It's unhealthy to not sleep enough. What are the forces? Gravity. And gravity, what?
Well, since it's not moving, right? So it shouldn't be equal to the tension force.
It's not moving?
Well, it just said it's suspended. Oh, so maybe it is moving actually.
Yeah. It will, okay, so, yeah, it doesn't say that it's released yet. So, yeah. If you were holding it, if you're holding the pulley to keep it from rotating, the tension would actually end up being bigger because the weight force isn't going to change, right? So whenever you released it, then the tension would slack a little bit. Yeah. Good point. But I think we are assuming that it's going to be released. So that's going to be MBG. And that's it. If this was an FRQ on the AP exam, you got some points there. We need to draw a diagram for the cylinder, though. And the cylinder will angularly accelerate. So we do have to draw the object when we do our free body diagram because the location of the forces on it are important. So here we're going to talk about a little bit of stuff that we haven't talked about quite yet. What forces are acting on the pulley? Cylinder. Tension. Now we need to draw it, though, at the point of contact between the string and the cylinder, which is right here. And it points down, and it is the same size as this tension force by Newton's third law. Let's talk a little bit more, though. Is that the only force? No. If that was the only force, the cylinder would be accelerating downward because it would have a net force pointing down. So what other forces are acting on the cylinder?
The force of the rod or whatever it is connecting it to the ceiling.
Yeah. And also the weight force, right? Mm-hmm. So let me draw the weight force too. So that'll be the mass of the cylinder times G. And then as Mr. Evans pointed out, there has to be a force that's opposing those forces to keep the pulley from translationally accelerating downward. And that is essentially a normal force, right? You got a post or some kind of rod that's maybe mounted on bearings, where the cylinder is actually resting on. So it's essentially a normal force, right? It's a normal force from the surface of the rod that it's mounted on pointing up. And since the pulley is not accelerating down, the size of that normal force should be equal in magnitude to the sizes of those two added together, right? So that normal force should be about that big. Okay. Why am I not too concerned about the weight force of the pulley and the normal force? Sometimes I am. If this is a large pulley on a skyscraper crane, and I gotta order the axle that goes in there to keep it from falling apart, then yes, I gotta know how strong of a normal force that axle is capable of exerting. But in more mundane situations or physics problems like this, why don't I care about the normal force or the weight force too much?
Because they're not on torque because they're on the axis.
Exactly, precisely. Neither of these forces is creating torque on the pulley because it's acting on the axis of rotation. Lever arm 0, therefore the torque is 0. The only force creating torque is that tension force there. Very good. Smart guy, I don't care what they say. Okay, so determine the magnitude of both the acceleration of the block and the tension in the cord. All right, well, they're asking for two things, so I'm assuming I need to generate at least two equations. Okay. We're experts, hopefully, at Newton's laws for translational motion now, so I'll start with the net force in the net force on this guy equals that guy's mass times the acceleration. Right, and that's just applying Newton's second law for translational motion, no big deal. I'm going to go ahead and define down as the positive for this guy because I want to have my net force be positive, right? And not have to deal with negative accelerations and stuff like that. So my net force, I have a positive MBG minus, now my tension force is negative within that coordinate system. That's going to be mass of the block times its resulting acceleration. Now we're asked to find the acceleration of the block and the tension in the cord. Both of those are in the equation. I do have the mass of the block. I do have G. But I have one equation, two unknowns. Therefore, I need another equation. So, I have a pulley that's going to be accelerating angularly, so I probably want to deal with the net torque on the pulley. So if I apply Newton's second law, net torque equals rotational inertia times the angular acceleration. Oh, I didn't draw my lever arm. Logan, you're supposed to remind me. Draw the lever arm. And what angle does the lever arm make with the tension force? 90 degrees. Always, always, always. And you might ask yourself, can I just do the net force on this guy to get another equation for the tension? Sure. I know the normal force is equal to mcg plus ft. But then I don't know the normal force. So that's the third unknown. Right? So I wouldn't need to get the torque equation anyway. If I use Newton's second law for rotation, then I don't need to worry about the normal force because, as Mr. Evans pointed out, it doesn't create torque. And so that's not going to be an unknown in the equation that I generate when I use Newton's second law for the rotation of the pulley. All right, so the net torque, and I'll write it up because I haven't written it up here in a while, but remember the definition of torque is force times lever arm times the sine of the angle between them. So here my force is the tension. I only have one torque, right? Normal force and the weight force of the pulley do not create torques. So I only have one torque, so the net torque is just the torque from the tension force. And that'll be the tension force Ft times the lever arm, in this case R, times the sine of the angle between them. But we know, because we've said it a million times at this point, especially if you're in pre-cal this year, or you were last year, the sine of 90 is what? You guys have all memorized the unit circle at this point, hopefully? Okay, yes sir.
For like showing our work on like FRQs and stuff, we have to show that sine of 90?
No, you wouldn't need to.
Okay.
If I was doing, I probably would just because I'm like kind of a completionist when I'm doing work like that, but you don't need to be. They know that by going from here to here, they know that you know that the sine of 90 is 0. Or 1. Sine of 90 is 1. But if I was doing this for a test, I would say FTR sine of theta equals rotational inertia times alpha. And then sine of theta I know is 1. So tension force times radius. Radius is the lever arm in this case, right? That's why I like to point that out. The pulley that we dealt with in the problem, the lab-based problem, the lever arm wasn't the same as the radius of the actual pulley, right? In this case, it is because it's just draped over the edge of the cylinder. So that's going to equal rotational inertia times the angular acceleration. Our problem now, though, just like it was with the lab-based problem, is the angular acceleration is now a different unknown. It's a third unknown, right? But remember, and I like to think of it as, if I have my pulley, and you have the string right here attached to the mass, well, this mass is accelerating downward with some acceleration A. this point on the string is also accelerating downward at the same acceleration. That should be logically obvious, right? Well, that string is also wrapped around the pulley, so that means the string on the pulley here should have an acceleration in this direction, but it should be the same, right? So take home point, every point on the edge of that pulley, and I've said this several times, but it's really important to understand. It makes your life a lot easier if you understand this. Any point on the edge of that pulley has that same acceleration. Okay. So I can relate the angular acceleration of the pulley to the linear acceleration of the block as it accelerates downward using that. Because I know that the linear acceleration equals the radius times the angular acceleration. Linear equals radius times angular. And then that tells me that the angular acceleration is linear acceleration divided by the radius. So then I can substitute that in there just like I did in the last problem. So tension force times R equals I acceleration over R. Cool beans? And then I have a system of equations. And if you're like me, and you're like, if I don't need to have a fraction, I'm not going to use fractions. So I'm going to multiply both sides by R. So I get tension force times radius squared equals rotational inertia times acceleration. So now I have two equations with my two unknowns. And you are free to solve this system of equations in any way that you'd like. I would probably solve this for the tension. Actually, yeah, I'd probably go back to, I'd solve this for the tension, which would make it a fraction again, and then just plug that in here, solve for the acceleration, and then go back. So if I solve this for tension force, I just divide both sides by the radius squared and get the tension force equals rotational inertia times... what did I forget? Let me go back to here. Tension force equals rotational inertia. Let me write it like this. I don't have a single value for up here, right? And this is where the algebra will start to get a little tedious. I got to substitute in an expression for it. And get used to the tedious algebra, because when we get to rotational kinetic energy, mechanical energy with rotation, we're going to have the initial gravitational potential energy plus the initial kinetic energy plus the initial rotational kinetic energy, which involves rotational inertia, equals the final of all that. So the algebra gets pretty heavy, so that's why it's important that you are careful with it. But yeah, I need to substitute 1/2 mr squared in for the rotational inertia. Hopefully we can see that this is the same thing as mass of the cylinder times r squared over 2. Because then you're not really writing it like a mixed fraction, which just makes algebra even way worse. This stuff's in the numerator, so you can put it up there. And when I write it like that, I see that ft times r equals, this guy's in the numerator, times the mass of the cylinder times r squared. No, what am I doing? Mass of the cylinder times r squared over 2 times a over r. If you're careful with your algebra here, though, you realize that your life actually gets easier. Because one of those r's cancels with that r. And I knew something wasn't working out. What's that? Everybody brought r. Yeah, so the radius doesn't even matter. So now I have an expression for the tension force. I was wondering why this wasn't happening. Equals mass of the cylinder times the acceleration divided by 2. So there Now this streamlines the process a little bit because now I have an expression for the tension force that I can just plug into this equation here. Right. So when I make that substitution into, let's call that equation 1, this equation 2. When I substitute this into equation 1, I get mass of the block times g minus mass of the cart times the acceleration over 2 equals mass of the block times the acceleration. Most students would, at this point, substitute in the values, but again, you're just as likely to have an AP exam question that has you calculate and determine an expression for the acceleration and an expression for the tension, in which case you would actually have to solve this for A. Okay? How would I solve this for A? Because I have two terms with A in them, with no numbers to put in. Put both terms with A's on the same side, right? So if I add this term to both sides, I get the weight force of the block will equal mass of the block times acceleration plus mass of the cart times acceleration over 2. And again, if you're like me, you're like, this would be a lot easier mentally with no fractions. So what can I do to get rid of the fractions here? Real easy. Multiply both sides, or multiply the entire equation by 2. In which case I get 2 times the weight force of the block equals 2 times the mass of the block times the acceleration plus, that 2 now cancels that 2 plus mass of the cart times acceleration. I like that better. I just feel better. Don't have to deal with the fractions. Then we have to do what? On the right side? Yep. The bad word, the F word, right? We have to factor. Yeah. Factor out the A on the right side. So I get 2 times the weight force of the block equals A times 2mb plus mc. Remember learning how to factor? Factoring quadratics. Oh, that's good stuff, huh? It's good times. And then I just divide both sides by 2 times the mass of the block plus the mass of the cylinder. It's time to retire this one. That's why I didn't play basketball. Alright, I'm going to erase the left side now. So all this cancels, leaving the acceleration by itself. So the acceleration of the block, and hence any point on the edge of the rotating cylinder, will be 2 times the weight force, or MBG, weight force of the block, divided by 2 times the mass of the block plus the mass of the cylinder. So if this was a symbolic question, which more often than not they actually are, that would be my answer for the acceleration. But we do have values here that I erased conveniently. So let's plug those values in just to get a feel for the actual numerical values for this kind of stuff. Mass of the block was tiny, right? 0.075 times 9.8 divided by 2 times 0.075 plus 1.5. So the cylinder is substantially larger, right? So we expect not a very big acceleration, right? You know, this is going to be a tiny number, but then it adds to a number that's going to be much larger. So we're dividing what is essentially a pretty tiny number by a much larger number because we got a very large cylinder with a lot of mass. So we expect a small acceleration, right? Whereas if the opposite was true, you'd get a much larger acceleration. If you get a much larger numerator here, and this isn't that much, then that numerator and the denominator are going to work together to have a larger acceleration. So it is important to be able to put numbers in, at least in your head, just to kind of conceptualize what you would expect. and then see if what you expect is what is actually borne out by the mathematics. And did you do it, Joel? Oh, you did it? What'd you get?
I got 0.8909.
0.89.
Forgot to times by 2.
0.89.
0.91.
091. I'll put 891. Meters per second squared.
You're still cool.
If that's wrong, it is Mr. George's fault. I'm making a video right now, so I gotta blame you. Alright, so that's the acceleration. It's not that fast. It's like 10 times less than this acceleration. That's why I didn't play baseball. Okay, and then if we know that, then the tension force is simply, we just take we can use either equation, but you want to use the equation that's simpler, right? Because it's just more convenient. If we had to get an expression for this, we would just plug in all this junk for the acceleration, which means it'd be mass of the cylinder divided by 2 times all that. And just so you know, on the AP Physics 1 exam, that's fine. If you had to get an expression for the acceleration and the tension, this would be a fine answer for that. Force of tension, mass of the cylinder over 2 times 2 mass of the block times g divided by 2 mass of the block plus mass of the cylinder. That's fine. Okay, you don't need to go any beyond that in any way. Yes, the 2 cancels that, but they literally won't take points off of that. But because we do have numbers here, we can just plug in this or that to calculate this tension. And again, we got a heavy pulley that's not rotating very fast, and you got a little tiny mass hanging on the end. So you expect that not to be too much tension in the string. So that's mass of the cylinder, which is 1.5 times the acceleration, which is approximately 0.891 divided by 2. Did you do that?
0.668.
0.668 newtons. Bien. This happens. This is why my brain was like, no, something's wrong. I forgot to do something. Oh yeah, I forgot to substitute in for I. When you do the algebra right, cancellate, and this is another reason that you don't want to plug stuff in the beginning, because there's so many cancellations. And I brought up conservation of energy with rotation, where you, instead of 2 terms on one side and 2 on the other, we can have 3 on one side and 3 on the other. And the algebra gets pretty heavy. But these kinds of cancellations, specifically with the radius or the lever arm length, they happen all the time. And so you want to do the algebra, you want to be careful with it, and you want to notice when everybody brings something to the party. You want to notice when things are in the numerator and denominator so you can cancel them out. And you want to intuitively, obviously, understand what's going on. Right? Notice this problem could not have been done until our rotation unit. You literally couldn't do it. You'd be like, well, how do I deal with what it's doing to the pulley? You know, how do I can't do it. Can't do it. Yes, sir.
Is that A equals R in your acceleration on here, and I just don't see it on the formula chart?
No.
No.
That's why I really stress. I stress. It'll be in your notes. I really stress. Remember this linear equals radius times angular. Right? When you're relating the angular motion of a rotating object to the linear or tangential motion of a point on the object, linear equals radius times angular. Linear velocity equals radius times angular velocity. Linear displacement equals radius times angular displacement. Linear acceleration equals radius times angular acceleration. So yeah, you can remember one thing that will encompass all 3. Unfortunately, it is not on the formula sheet. Also, unfortunately, it's used pretty often.
Is there like an equation that you can derive that?
No. That it stems from something that you learned in geometry. Remember, it stems from arc length equals radius times angle. Right. Divide both sides by time. You know, arc length divided by, that's length divided by time, that's velocity. Theta divided by time is angular velocity. Right. Divide both sides by time here. velocity to change in velocity. Really, it should be change in velocity over time is acceleration. Angular velocity, change in angular velocity over time is angular acceleration. So it stems from the geometry that you learned years ago when you're a small child. You know? But yeah, unfortunately, it's just something that's not on the formula sheet that is used fairly often.
Disregard for the AP test. We're not going to use like any of the electricity, right?
Nope,
They cut that out.
not this year.
Right, sweet.
Or the waves. Waves is good stuff. The physics of waves, it's incredibly useful. All right, that's it. Everyone home.